Welcome to the seventh problem solving session for this course. So, of week 7 this week, and in this problem solving session, we'll look at some sample problems, specifically the assignment problems of previous offering of this course. So let's go to the whiteboard. Okay. I hope you can see the screen.
Yes, visible.
Okay. So in this week, we have seen a couple of techniques, miscellaneous techniques. In fact, there is a chapter in this book called Miscellaneous Techniques, and the content is from this chapter. So we have seen dynamic programming and integer linear programming techniques. So in some of the previous sessions also, we have some questions on how to compute different entries in the DP table. So the questions in this session will be also of similar flavor. So there are questions on different problems, and we are looking at some DP tables, and we're asking that what are the missing entries in this DP table. So basically, if you have seen the videos and if you know how the recurrences of the dynamic programming are defined, then you will be able to uh, understand what is going on. And even if you haven't seen the videos, I will give you some background on uh, uh, how the dynamic programming recursion is defined. So I think it wouldn't be a problem. Okay, so the first problem in today's session is related to set cover. So let us recapitulate what is a set cover. So in the set cover problem, there is some issue with my marker. I think there is some. Let me just charge it for a few seconds. See if it works now. Yeah, it's fine. Okay, so in the set cover problem, again, it is not working. So we have a family F of sets over a universe U, and we have been given a budget K. So you can think of the universe as a set of elements. Some elements appear in the universe. So this is the universe U, and you have a family of sets over the universe. So therefore, let us mark. Okay, let us say these four elements together is one subset in the family. These are contained in another subset. There is another subset. Maybe these two are in another subset. So subsets are defined out of the elements of the universe. And what is your objective? Your objective is to pick a subfamily. That means to pick some of the subsets, a subfamily H of F of size at most k. So you're allowed to pick k subfamilies such that the union of these subfamilies covers the entire universe. This definition we have seen before. So to solve this problem, uh, there is a dynamic programming approach which has been discussed in the videos. So before I go to the definition of dynamic programming, let us directly go to the question. Then we can visualize things better because we have some numbers. Okay, so let me make it slightly bigger. So this is a question. So your universe is a set of four elements, A, B, C, D. So the universe is a set of four elements. And you have some subsets formed out of the universe. So first subset is S1. So S1 is nothing but AC. So this is S1. S2 is A and D. S3 is B and D. And S4 is B and C. Right. So because it's a small example, we can just look at it and we will be able to tell what is the minimum sized set cover. You want to take any guesses?
So if we take the union of S1 and S3, say the value of k is equal to 2, if we take these two subsets, then this will cover the entire set.
Exactly. So because let's take some another color. So S1 is A and C, and S3 is B and D. So this is a valid set cover because these two sets together covers the entire universe. And can we get a smaller set cover? That means, is there only one set that covers the entire universe?
Uh, a single subset cannot cover the entire set, or otherwise, I mean, we can have a different solution. We can take the union of S2 and S3, but at least two subsets are required.
We can take S2 and S4, yes. Right. So this is a minimum set cover, but the question is asking that how does the algorithm proceed? So there is a dynamic programming algorithm we have seen in the videos. So the question is just a warm up for you to appreciate that the dynamic programming table will be able to let you arrive at the same answer that the set cover size for this instance is actually 2. So let's read the question. In module 7, lecture 31, we use dynamic programming to find the minimum number of sets from mathcal F required to cover mathcal U. Recall that for every subset of the universe X and every index J, where J lies between 0 to mod mathcal F. So F is what? F is the uh, family. So this family has 4 uh, sets in it, subfamilies in it. So mod F is 4. So J, as you can see, varies from 0 to 4, and X is all subsets of U. So because mod U is 4, so the number of subsets of U, the power set of U has cardinality 2 to the 4. So 16 different rows are there. So for each of these rows and columns, there is an entry in the DB table. And we'll look at how the DB table is formed in a moment. So let's read the question. So for every subset of the universe and every index lying from 0 to mod f, our algorithm computes and stores a value corresponding value in the table. So table is denoted by pi. It's calling the table as pi. That entry x comma j in the DP table corresponds to the minimum number of sets from fj. Fj is the first j subfamilies in F, so S1 till Sj, that are required to cover X. So basically, we are asking, so pi xj is asking that, okay, I do not want you to cover the entire universe. I want you to cover a subset of the universe, which is X. And how many sets will you pick? What is the minimum number of sets you will pick from Fj sets to pick from Fj? Fj is nothing but the first j families in the set F. and you want to cover partially only. So cover X, which is a subset of the universe. Okay. So as you can see that for the entire universe, the minimum set cover will be given by the entry corresponding to. So this is the size of the minimum set cover for the universe for this instance.
So what will be the meaning of F1?
What is the meaning of
F1,
S1
say
only?
F1, F, okay,
Yes, yes.
F1 is S1 only. Okay, all right. Fine. So J, but then J varies from where to where? J varies from 0 to 4.
J varies from 0 to 4. When you are saying F1, so J is equal to 1.
Okay, but then J can only vary from 1 to 4 and not from 0 to 4. So what is the significance of 0 here?
Significance of 0 means you're not allowed to take any subfamily. So that is a trivial case, or rather, this is a base case that, okay, you're asked to cover a subset X of the universe, but you're not allowed to take any subfamily. So in that case, we're saying that we are in this domain where J is 0. So basically, J is 0 is this uh, column. In this column, you can see that, okay, if you're not covering anything, that is phi. If you're covering only nothing, then the corresponding entry is 0. But if you want to cover even one of the elements of the universe, then you don't have a feasible solution
Hmm.
because F0 is essentially nothing.
Okay, okay.
Okay, so we are fine about what is the meaning of every cell in this DP table, that is pi of x comma j. So pi of x comma j is nothing but the minimum number of sets to pick from f of f sub j such that all the elements in X is covered.
So like say the entry corresponding to the row number 14 is 1, 1. Against the value of j is equal to 3 and the value of j is equal to 4. So what's the interpretation of this row then?
So this means that if you are willing to only cover B, you are willing to cover B only, then and you are allowed to take, so this is the cell corresponding to j is equal to 3. So you are allowed to take S1, S2, S3, but not S4. Then it is possible to take one of S1, S2, and S3 and cover B. So we can say that, okay, S1 is not covering B because it has A and C. S2 also does not contain B, but S3 in fact contains B. So it is possible to take S3 and cover B, and S3 is one subset only. So therefore, it means that one subset out of S1, S2, S3 is sufficient to cover B.
Okay, okay. So one subset out of S3 and S4 is sufficient to cover B.
No,
And
no, one.
now the value of the 11th row becomes 2. So how it becomes 2? Because we require uh, 11th row becomes 2 because since we require uh, two two subsets out of S3 and S4. No,
No,
that
out
is
of
not.
S1, S2, and S3. So this is corresponding to J is equal to 3, this column. So you're allowed to take S1 or and S2 or and S3.
Okay. And what are the values of S2? Can you slightly scroll it down slightly? Thanks for that. Thanks. So the value of S2 is so okay. So out of say here the value becomes 3. So we require two subsets ranging from S1 to S3 to cover AB. And the next row also is 2. So we require two subsets. Fine. Ah, yes, yes. All right. And the sixth row, again it becomes 2 for CD, indicating that from S1 to S2, I require 2. Yes, it is right. Yeah, thanks, clear. Yeah.
Okay. So now let us look at what is the rule that we have to follow. So actually, I should have numbered these rows bottom up. I am numbering top to bottom, but anyway, so this is the row that is computed first. So this row is saying that if you're not allowed, sorry, if you're supposed to cover nothing, then you do not require to take any sets at all. So zero sets out of S1, S2, S3 will be sufficient to cover nothing. So that is the base case. And this is also the base case, this column. So this is corresponding to asking that if you are not allowed to take any subsets from S1, S2, S3, and S4, then what can we do? So we can only cover nothing. But if you want to cover anything non-empty, that won't be feasible. So all these infinity entries are corresponding to that. So, so the question is, how do we compute a given x comma j? So for that, this is a recurrence. So I hope you are able to see the recurrence. So the recurrence is, let's look at the base cases. The base cases are simple. That if you're willing to cover some non-empty thing, non-empty subset of the, so I'm saying t, but t and pi are saying, I mean, let's think of things as pi. They're saying it's pi. So the name of the table is pi. So this is saying that, okay, if you want to cover something non-empty, but you're not allowed to take anything, then that is not possible. This is one base case. The other base case is if you're not intending to cover anything and you have nothing to cover, then that is fine. You can just say zero. The recurrence is the following, that if you want to cover some x using S1, S2 up till Sj, then you can do two things. Either you pick Sj that covers some of the elements in X, or you do not pick Sj. Okay, so this is the situation when you pick Sj, and this is the situation when you do not pick Sj. So out of this, so first let's analyze what is the meaning of this. So this says that, okay, you have picked Sj. So one subset is taken. That is why correspondingly we have one plus, because we have taken Sj, now we are intending to cover the remaining elements, that is X minus Sj, with Sj is already picked with subsets S1 through Sj minus 1. So therefore, this entry plus 1 will be our estimate if we are picking Sj. And this entry is already in the table, remember, because we are constructing this table bottom up. So this entry is corresponding to some smaller set than X. So smaller sets are in the lower rows of the table, and the lower rows are already computed. So instead of 1, 2, 3, 4, like 16, this way I should have written, let me just write it down. The rows should be numbered bottom up. So this is row 1, 2, 3, dot, dot, dot. This is 15, this is 16. Okay. So this part is clear that if we pick Sj, then our estimate for the minimum set cover for X using S1, S2 up till Sj is this. If we do not pick Sj, then we have not covered anything. So we are still intending to cover all the elements in X, but we have not picked Sj. We have decided that we will not pick Sj. Therefore, we are allowed to pick anything from S1 through Sj minus 1. Therefore, this is the corresponding entry. So is this recurrence clear?
Yes, yes.
Okay, let me check the chat box if there is any question. Okay, I think it is clear to everyone. There is no questions in the chat box. So there are only two options. Either you pick Sj or you do not pick Sj. And correspondingly, you have the entries. and these entries are already computed. Therefore, to compute a given entry in the table, you just have to look up two entries which are already computed. So you have a constant time operation. In constant time, you can find out a particular entry, and then you take the minimum because you are willing to find the minimum number of subsets to cover X. So you are taking the minimum. Fine. So what is the question we are asking? So we have been given the table. So let me ask the question. So the question is the following. So far, we have only seen how the table is constructed. The question is, which DP table entries do we look up to find the cell corresponding to ACD, comma 3? So let me write down the question. The question is, which DP table entries do we look up to compute or to find the entry corresponding to the subset ACD and the index 3? So that is the question. So we are willing to find ACD and 3. 3 is this. We're interested in this entry. So which two entries that are already computed do we have to look up?
So what is there inside the subset S3?
Okay.
So S3 is BD, right? And we have to find this ACD thing. So therefore, therefore I can go for the first part of the recurrence relation. So since S3 is BD, so at least D can be taken from here, resulting into only to find the AC with the two number of the sets. So AC with AC and then 2. AC and 2
Okay.
here.
So AC and 2 is this one.
Yes. And now since 2 has, I can take A from S2, resulting into I need to find D comma 1. So D comma 1 is, but this entry is infinite. Why so? AC and then 2. So I can take A from here and then resulting into C comma 1. And C comma 1 is 1, right? So this entry has to be taken. And 1 contains the element AC, so C can be taken from here. I think only this is required.
No, so this entry I understand. So this entry is corresponding to taking S3. Yes. So once we have taken S3, then which elements are covered?
D
B
is
and D are B and D is covered, but we are only intending to cover ACD to forget B. So we are covering D because we are going to include S3. Now we are left with AC. So I understand that, okay, for AC, we're already taking S3. So till S2 we can take. So I can understand that AC comma 2 is an entry we have to look up.
yes,
Okay.
because that is already there.
So this is sacrosanct. So this we will mark correct. So AC comma 2 will mark correct. Now, if we do not take S3, that means we have not covered anything. So we have decided that S3 is not going to be taken. So now we are allowed to take up to S2 only. So but we are still looking for covering ACD. So ACD and 1 and 2, we can take either we can take S1, S2 or both of them, and we are willing to cover ACD. Okay, right. So this is the entry ACD comma 2 that we should be looking up, isn't it?
Yes. So actually, this discussion, I mean, probably, yeah. Now it is slightly difficult to understand. So ACD and then so ACD comma 2. Uh, so we are computing the value of ACD comma 3, is it?
Yes, yes. We're
Okay, so
computing
if we are computing
this
ACD
right.
comma 3, then if I do not consider S3 at all, so if I do not consider at all, so then I'll have to find the value of ACD comma 2.
Yes.
So yes, this one. So if I, but then how will I decide that whether to consider S3 or not?
You
Because
take the minimum. You take the minimum of 1 plus taking S3, comma, not taking S3. You take the
so
minimum.
if I take if I take S3, so
Yes.
what is the value then?
1 plus
The
1.
1 plus 1. Yes. And so should I break the tie in favor of what? In favor of the
Yeah, you don't
left
have
node?
to. So there is no tie breaking involved because the table is not asking that what are the sets you are going to pick. The table is asking what is the number of sets you are going to pick. So both values are in fact corresponding to 2. So you can just populate this entry of the table as 2.
Yes, yes, that's right. Now I understood you. Clear.
Yes. So it's not a question of which are there are possibly many set covers of same minimum size, but the question is what is the size?
Yes.
So as you have already observed initially, that you can take AC and BD, you can also take AD and BC. Both are valid minimum set covers in this case.
Yes.
Fine. So the question was like this. So so the point is the nice thing about this dynamic programming tables is that the table size is fixed. The table size is the number of rows into the number of columns. So now if you can compute every entry of the table quickly, so in this case, looking up two entries and then comparing them to find which one is the minimum. In fact, one plus one table entry and the other, which one is the minimum. In constant time, in very little time, quickly, we are able to populate other entries. So basically, the running time of this algorithm is proportional to the size of the TP table.
But then as we increase the number of the elements of the set, the table size will grow quickly. In fact, the table size will grow exponentially in terms of the number of the elements in the set.
Yes. So whatever is the universe size, so 2 to the u times the number of uh, sets in the family. That is the table size you have to
Yes.
construct.
So I don't think that this would be an efficient solution. Even though it's true that we are using a bottom-up approach, and everything. I mean, at any point of the time, whatever we require would be available to us from the lower entries. But the table size since would be huge, so
No, the table size is limited. So the idea of this parameterized algorithm is that whenever you are saying that, okay, my running time is fixed parameter tractable FPT, so you are expecting that the parameter size is small. So you were expecting that if the universe size is small, then this algorithm will work fast. That is the expectation. I understand your point. If the universe size is very large, then this algorithm is meaningless. But if the
yes,
universe size is small, which is what is our expectation, then this is fixed parameter tractable by the parameter universe size.
yes. So are there studies available that to what extent the tractability would be there, and beyond that point, the problem will become computationally intractable?
So if the so for the set cover problem, the best we can do is find a log n approximation. So do you understand what is an approximation?
Little bit.
Okay, let me
Uh,
just give you a primer on that. So I'll just go down slightly. So for the set cover is one of the hardest problems in the theory of approximations. So it is a classical problem out of the uh, set of NP complete problems given by Gary and Johnson. So set cover is known to be inapproximable below logarithmic factor. So I will explain what it means. So that means that let us say for a given instance, so a set cover instance is nothing but an a set cover instance is nothing but an universe U, a set of families which are formed from the universe. And in the optimization version, you are asking that what is the minimum number of sets you want to pick from F so that U is covered, right? So if let us say that the optimal number of sets is OPT, this statement is saying this statement that set cover is known to be inapproximable below logarithm factor is saying that there cannot exist an algorithm. There cannot exist an algorithm that there cannot exist algorithm, let us say A, such that the let us say algorithm A outputs a solution sol. This so there cannot exist an algorithm A such that the solution sol output by A, the solution sol output by A is such that the size of A. So remember what we are outputting. We are outputting a set of families. So the minimum number of sets that you have to pick is OPT. So let us take some numbers. So let us say OPT is 100. So minimum 100 you have to take. So what this inapproximability result is saying that no algorithm can give a solution sol such that the solution size is better than better in the sense less than log n, actually order log n times OPT. This is ruled out. Okay, so n is the what? N is the universe size. So just take some numbers, then it will be easier. So let us say that n is 2 to the power 10. Okay. So there are 1024 elements in the universe. So what is log of n? So log of n is, let us say, base 2. Log of n is 10. So if the optimal number of sets you have to take 100, then no algorithm can give you 1000 out of the order of 1000 sets that can cover all the elements. That's what it's saying. So it is so difficult that you cannot even imagine to be very near to the optimal solution. So what it is saying that okay, if the universe size is constant, then I give you an algorithm which runs in polynomial time. So 2 to the power running time is 2 to the power u, something, some polynomial into some polynomial. So if the universe size is constant, so it is giving a polynomial time algorithm. But if the universe size is large, then of course you are right that no algorithm can in fact be any close to the optimal algorithm in polynomial time.
Yes. So, how to know that for this problem FPT exists or not? I vaguely remember that there are problems for which FPT doesn't exist. Probably traveling salesman problem is one of them. And for some
So the
problems, this FPT thing exists. So how to know that? I mean, how to classify this thing?
so there are problems for which fixed parameter tractability is not achievable. So there are problems which are not fixed parameter tractable. So your question is how to identify if a problem is fixed parameter tractable or not. That is the question, right?
Yes.
So first, whenever you have a problem, so along with the problem, you specify the parameter. So you specify the parameter, and you are asking, for example, so far we have taken the solution size as parameter. Sometimes we have taken the tree width as a parameter. So with respect to that parameter, whether there is a fixed parameter tractable algorithm or not, that is the question. So then there are reductions. So there are some known fixed parameter. Sorry, there are some known problems which are not fixed parameter tractable. So FPT complete problems. So there is some theory of hardness. So some problems are known as W1 hard. So if you can show that there is a reduction from an already hard problem to the problem you are interested in, uh, just a second, let me recall if I'm saying the correct thing. So you have a problem at hand. You want to decide its hardness. So you will compare it with the hardness of an existing problem. I mean, an existing problem which is known to be hard. So you reduce, yes, so you reduce, so that means you convert the instance of the hard problem into your problem. Okay,
Yes, because then my problem would be at least as hard as that
yes,
problem is, which I'm reducing
correct.
to it.
So you have some known hard problems. So from a given hard problem, you reduce it to your problem. So that means that hard instance you convert to your instance, and we will see it. So there will be a week in which we will talk about the hardness of fixed parameter tractable problems. There we will be able to decide. We'll see some reductions that okay, this problem is not fixed parameter tractable given the parameter. So it is very important in this theory that we make statements with respect to the parameter because there could be many different parameters.
So what these parameters are? Like in this case, what is the
Solution.
parameter?
So in this case, the parameter is, I think, the universe size, because as you can see, the table has how many rows? The table has mod u rows. So for every subset of the universe, you have a row, and therefore you cannot. So the running time is 2 to the mod u times mod f. So here the parameter is mod u, that is the size of the universe.
Yes. Now I understood. Yeah.
Okay, so the question was, so the questions in the assignments or exams will be like this. So, okay, if you have understood the algorithm, that how the dynamic programming table is constructed, then you know that to populate the entry or compute the entry corresponding to one cell in the dynamic programming table, you have to make some lookups, probably some small number of lookups. So this question was asking that, okay, to compute this entry, which all uh, cells will you look up? This is the other one. Right? So ACD comma 2 and A comma C comma 2. These two tables entries have to look up. So one can cook up many kinds of questions. So this is just to give you a flavor of what kind of questions are expected in this dynamic programming table uh, computations. Okay, fine. So I think we can move on to the next question. But yeah, so the next question is on Steiner tree. So if you watch the videos, then you will be able to understand the question. So I think I have to. I'll still give you a primer on what is a Steiner tree. Okay, so in the Steiner tree problem, your input is a graph, and there is a weight on every edge. So you can think of the graph as an undirected graph, and there is a weight on every edge, a positive weight, positive real weight, and you have specified that some of the vertices in the graph are spatial. So such spatial vertices in the graph are called terminals. Okay. So what is your objective? So your objective is to find a connected subgraph H of G that contains all the terminals in K and is such that the weight of the edges in that subgraph is minimized. So basically, you can see that maybe you can take an example. So maybe these are the cities. So these terminals are sort of metro cities, like large cities, and you would like to have good connectivity among these metro cities. But these metro cities are not directly connected to each other. Maybe they're connected via smaller cities, and these smaller cities have also connections, some roads. And your objective is to make sure that there is a connected subgraph connecting the terminals, and you want to choose this subset of edges. Okay, and so these are sort of, maybe you want to make highways such that your cost is minimized. So in this case, all the edges can be thought of as having equal weight. Let us say in this case, all the edges have equal weight, weight 1, but weights could be different. For simplicity, let us say that the weights are equal. And these red vertices are the terminals. I want you to find a subgraph of edge. That means I want you to find a set of edges so that this constitutes a connected subgraph connecting these three uh, metro cities or terminals. So is that question or is that a description of Steiner tree clear?
Yes, it is similar to the minimum spanning tree problem, except that some of the vertices have been explicitly marked, and those
Yes,
vertices need to be covered in the trap itself.
exactly. So as you can see that we are minimizing the weight of the edges in the subgraph. We are definitely looking at building a tree that doesn't have a cycle, because if you have a cycle, we can always get rid of one edge in the cycle, and that will further minimize the sum of the weights. So in this case, let me give some names to this smaller vertices. So just say that this is maybe A, B, C, and these are like, what should I call this? We will just say numbers 1, 2, 3, 4, 5, 6, 7. So we want to connect, we want to choose edges. So clearly, if we want to have any connection in the graph with A, so this edge has to be taken because A is a vertex with degree connected at all. Its only edge must be taken. So let us take this. B also is a uh, uh, vertex with degree 1, so this edge has to be taken. But for C, there are choices. For C, you can pick some of, you have three possible edges that you can choose. But the thing is
So
that
now,
if you,
so now I have doubt here in this Steiner tree that do we have to cover all? No. So we have to find what? We have to
the
find the
connected, you have to find this. This is the goal.
So what's the meaning of the connected subgraph?
So connected subgraph means you have a set of edges. You have a set of edges, and every, so connected subgraph means every vertex is reachable from every other vertex in the graph.
Okay, okay.
So basically, you want to make sure that A and B are reachable. So that's why definitely you have to take edges. So there should be at least one path from A. There should be at least one path from B to C, and there should be at least one path from C to A. And then you want to minimize the number of edges in this case because every edge has equal weight in this case. So
So so
how about
the so the minimum weight would be equals to 6 here.
correct? So this is a valid Steiner tree, but we do not know if it is of minimum weight. Why is this a valid Steiner tree? Because A and C are connected. There is a path from A to C. Every pair of vertices, terminals is connected. But can we get better than C? Can we get maybe, how about, so one can delete, maybe one can delete these two and take rather these two, but it doesn't help. It doesn't help much because anyway, so there is no way to get rid of two sort of edges and pick one edge. No, sorry, sorry. This is not even connected. This is even more. Uh, 6 seems unavoidable. 6 seems unavoidable. Right. So anyway, so this is a standard tree problem, and the question is, now we can look at the question. So now that you understand the definition of standard tree,
But I have a doubt here that in the minimum spanning tree, we have to find the acyclic subset of the edges connecting all the vertices. And
correct.
here in this case, we have been given only selected vertices.
Yes.
So how this problem? I mean, what makes this problem intractable? Whereas the spanning tree is very much solvable in the polynomial time.
Okay. So why is this problem intractable?
Yeah.
Let me ask. I don't know. So standard tree intractability. Wait just a second. Okay. So there are reductions from known intractable problems to standard tree. But your question is different. So what is the intuition behind its intractability? That is the question, I think, more than giving a technical answer.
Yes. Because in case of MST, I mean, we need to find the edges covering all the vertices. Clearly, whichever vertices have been given here would be the subset of all the vertices. So if I can solve a problem having all the vertices in the polynomial time, then what is stopping me to solve the problem with solving the problem with the selected vertices?
So I think having all the vertices, so in a minimum spanning tree, you are willing to connect, you're willing to get a connected graph, a cyclic graph, so that all the vertices are connected. So that liberty of, choosing edges such that all the vertices are connected has something to do with its tractability.
Yes, yes, yes. So probably it could be like say, because in the case of the standards tree, since we have to definitely go through certain number of the vertices, and then we have to minimize the sum of the weights assigned to the edges connecting those special vertices. So probably since this time we have to minimize the sum of the weights assigned to the edges connecting the special vertices, which might be making this problem computationally intractable, because this problem may become somewhat similar to the Hamiltonian circuitry then, wherein we have to, I mean, the Euler circuitry is tractable, but the Hamiltonian one is intractable, maybe because of, I mean, something similar to that. I'm not sure. Yeah.
Let me spend a minute or so if I can give you a satisfactory answer. you can compute an Eulerian circuit, but Hamiltonian cycle is NP complete.
Yes, yes.
So you had asked one more question last time, that why did they define tree width the way they defined? So I had looked up about it also.
Okay.
Just a second. So I am not able to give a satisfactory answer why standard tree, what is the intuition behind standard tree being intractable, whereas the minimum spanning tree is a simple algorithm, greedy algorithm. Uh, but yeah, so let me park it for next session. I'll just look at the
Yes,
reduction.
yes, 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 sure, sure. But your this direction seems to be slightly convincing to me that here we have to work with the special vertices and we have to minimize the sum of the weights of the edges going through these special vertices. So since some kind of the speciality is here, so that is putting some kind of the restriction here,
Constraints, yes.
constraint here, and thereby making the problem intractable, probably. Maybe, yeah. But we
Yes,
can
so
discuss next time. Yeah.
so we had seen the definition of tree width. So in the tree width definition, so basically the way it was defined, that for every edge UV in the graph, you wanted to have a node or bag containing, there should exist a node or bag containing both U and V, U and V, and we wanted that for every uh, U in the graph, that is every vertex in the graph, we wanted to have the bags should be connected in the tree, in the tree decomposition. So this was the definition. So I looked up the definition, and it looks like that the idea of tree decomposition and everything is not very old. So 1972 onwards, we have uh, this literature on tree width. So what I answered last time is probably correct, that the definition is just to sort of assess that how similar a graph is to a tree. And once we can make that assessment, so many of the problems which are applicable for trees can be solved, sometimes efficiently or sometimes approximately. So from algorithmic perspective, if you can uh, convert a graph into a tree-like structure, then many of the algorithms can be applied and many of the problems can be solved.
Yes, yes, yes. So if we go for this tree decomposition of a graph, and this implies, does this imply that whichever connections are being maintained within a graph are also being maintained within a tree, and no other redundant connections have been introduced while converting this graph into this tree? Is this the case here, that we are putting all those vertices which are connected in the graph within a same bag, and then we are maintaining the connectivity among the bags also? So while maintaining the connectivity among the bags, are we introducing some redundant connections which were not there in the graph in the
So the
beginning at the?
question So the question is, if there was a vertex U and there was a vertex V which are connected by a path, uh,
Yes,
and there was a vertex W which was not connected to W, then whether uh, all the nodes in the tree decomposition containing W are separate from the nodes containing U. That
yes,
is not
yes.
that is not true, because we have a tree, and in the tree all the bags are connected. The question is, yeah, maybe Yeah, so maybe so yeah, so far, so all the graphs that we have seen, the path graphs, cycle graphs, we have only looked at connected graphs, and from connected graphs only we have gone to a tree decomposition. So the this kind of a situation will not arise. So you will anyway be connected to W. So that is why in the tree decomposition of also the connectivity will be preserved. But
Mhm.
if there are vertices U and W which are in separate connected components, then of course there would be separate trees, right? I don't know. Let me think about it. So there is a vertex U in a connected component. There is a vertex W in a connected component. So U and W are definitely not in one node, or maybe
Because this decomposition need not to be unique.
this decomposition is definitely not unique. We are
Hmm.
interested in either reducing the back size as much as possible, and there was some definition of nice tree decomposition also, where we had certain other constraints.
Yes, yes.
So whether connectivity is preserved or not, I have to again give it a thought.
Yes, because if in this process, if we either, I mean, definitely we won't be losing connectivity because we are converting the graph into the tree.
Correct.
Uh, so, but since the graph by default is connected, or most of the graphs we consider are connected, so but this connectivity issue can may not be that much relevant. But if we are introducing many more connections which were not there in the original graph, so we are trying to, so indirectly we are trying to apply those algorithms which are exclusively meant for the trees at the cost of introducing many more new connections. So how can this be beneficial? Yeah, that is the question.
Whether new connections are formed or not, that I'm not sure.
Yes. Yes.
So
Yes.
you have to be more precise. Like for example, the question is only valid when there are multiple connected components, and then we want to see that whether vertices from different connected components got connected via bags or not.
Yes. Yes.
So I think that is unlikely, but then I won't be able to give you a you know uh, final answer today. So let's give it a thought, and then we'll see it next time.
Yeah. Yeah. Sure. Sure. Sure.
Okay, so the Steiner tree definition is done. So let's look at the question that we're interested in. I will get the question. This is the question. Yes. And this is also part of the question. Yes. Let you look at the question, and meanwhile we'll take a 5 minutes break because it's already
Yes.
1 hour.
Yes. Yes.
So yeah, this is the question. We'll solve this question after 5 minutes. And I have to write down the questions. So I just pick the pictures. So the question is to find the missing repeatable interest. So there is a missing link. So we have to find this. In fact, I have to tell you what is the recurrence relationship. Otherwise, you won't be able to read. So let's resume after 5 minutes. Then we can discuss it.
Yeah. Sure.
Let's start again.
Yes, yes.
So I hope you had a chance to look at the question. So we have a graph. Uh, so in this graph, there are 1, 2, 3, 4, 5, 6, 7 vertices, and 3 of the vertices are marked as terminals. So we want to be able to pick edges such that these 3 vertices are connected, and we are using dynamic programming to find the minimum possible weight of a standard tree. Here you can see that the edges are having non-uniform weights, so we want to find the minimum possible weight standard tree for these 3 terminals. Okay, so recall that for every non-empty subset D of K and every vertex in the graph, uh, K, why is K here? Oh, it should be minus K, I think. Just a second. Right, so there is a minus here, Vg minus K. This is Vg set minus K. So there is an entry Td comma V corresponding to a D, which is a subset of the terminals, and a vertex V, which lies and which is a non-terminal. For every non-terminal and every subset of the uh, set of terminals, there is an entry in the TP table. And what does this entry signify? So this entry means it is the minimum possible weight of a Steiner tree for connecting this subset of terminals as well as V. So correct. Right. So let me just write down the recurrence first. So the recurrence is the following. So what is the question? Oh, let me write the question. So find the missing DP entry. So what is the missing DP entry for? So we want to find T of K1, K2, K3, comma D. Okay. So this is the row for D. Sorry, this is the column for D. This is D, and this is the row for K1, K2, K3. So we do not know this. So we have uh, already computed the entries bottom up, and we have already computed this. So what is the value of this? So this is corresponding to the minimum possible weight of a standard tree that has K1, K2, K3, and D connected.
So, will it be like, say, similar to the previous case? So, can we write it as the minimum of the T of the K1, minimum of the T of the, uh, yeah, I was just trying to guess, but then probably would be different. Yeah.
That's fine.
So the thing is that the second possibility could be that we do not consider the vertex D at all. So if we do not consider the vertex D at all, this vertex at all, I mean,
Okay.
how to, if we do not consider it, so what could be the meaning that the shortest distance of the terminals will not make any sense. If I, so instead of removing D, instead of not considering D, better we not consider one of the terminal here. So will
Correct.
it be like, say the T of K1 comma K2 comma D plus something? Will it be like? I mean, I do not know the relation,
Correct.
but
Correct. Yeah, yeah.
yeah.
So you're sort of guessing in the right direction. So you have not watched the video, so you won't be able to get the exact recursion. It is slightly tricky. So let me write down the recursion, but you are sort of thinking in the right direction. So,
Okay, okay, yeah, thanks.
so here is let us say, this table is called T. Yeah, they are saying this table is called T. There is a T. So T of this thing will be equal to minimum over or let me just write it this way. This is equal to minimum over. So you consider a partition of T. So in this case, T is K1, K2, K3. So these are the set of terminals. So you consider a partition of T. So you partition the terminals into two parts. So maybe this is one partition. K1 is one partition and K2 and K3 in another partition. Or maybe these two in one partition and this is another partition. Or maybe this is one partition and this is another partition, like that. Okay, such that D1 intersection D2 is empty. So this is disjoint partition, and you have to take the minimum out of T of D1, comma, so V. So V is over all the non-terminals. So the set of terminals is uh, the set of terminals is K. Okay. So recall that K is the set of terminals. So you take V among the non-terminals and plus D2 comma V plus the shortest path distance between V and, in this case, we have D. Okay, so this is the recurrence. Right, let me verify it once if I'm reading the right thing. Okay, fine. So how many, in the previous question, to find a particular entry, we just looked up two entries. So in this case, there are many entries to be looked up, but not too many. So first of all, what are the possible values of D1 and D2? So let's look at that first. So let's make a table. D1, D2, and V.
Four.
What are the four? This thing?
Four. So say like here, this set is the set of the terminals is having three elements. So there would be four subsets of this set. Uh, there would be four mutually disjoint subsets of this set.
Okay. What are they?
K1, K2, K3 all alone and a phi. Because now if we consider D1 as K1 and D2 as K1, K2, so the intersection of D1 and D2 won't be equals to phi.
Okay, so basically, yeah. So if you consider one more entry as phi and K1, K2, K3, then we will replace this with phi. Let me just write it. So here we'll have phi, and here we'll have K1, K2, K3. But we don't have. We could actually do that, but we don't have the entry corresponding to. So for K1, K2, K3, we have entries corresponding to ABC, and we don't have an entry for D. So, but for all other rows, we have all the entries.
So first,
So,
first, first row seems to be incorrect here. K1 and then K1, K2. It has to be something else. K1 and then K2, comma K3.
oh yeah, that's a typo.
Yes, yes.
So we are specifically considering three possible partitions because this partition we do not have all the data. So let us not worry about this partition. So the other, so yeah, so there are three possible ways to partition the terminals, but then again there are four different non-terminals. So corresponding to that we'll have A, B, C, D. So A is this is a set of valid subproblems for which we have entries here. So for example, K1 and A, this is an entry, and K2 and A is this is an entry, K3 and A is this is an entry, again K1, K2, A. So the point is three entries per non-terminal. So four non-terminals are there. So 12 entries altogether we have to look up. Is that understood?
So I'm comfortable with the three entries, but not about this 12 thing. It's just because, say, we are having three uh, subsets, and then the possible values of v could be what the small d here is.
Small d is vertex.
Okay, yes, yes. Fine. So since we can have four different possibilities for the value of d, so therefore 3 into 4, 12.
Yes. Yes.
Yes, yes. Clear, yeah.
Yes. Now we just have to look at the distances, the pairwise distances of D with the non-terminals. So let us compute the distances. So distance of, let us say, non-terminal A with D is what? Distance of non-terminal B with D is what? So we are looking at the shortest path distance. So distance of non-terminal C with D, distance of non-terminal, what is the other non-terminal? Yes, D and D, that is anyway 0. Yes, so A to D. So A to D, this is 2. Yeah, so A to D is direct edge and that is the shortest path. Let's mark that 2. How about P to D? A to D, that is 3. This way it is 3. This way it is 4. So that would be 3. How about C to D? That is direct edge of only one. Wait, this is okay. Now we can look up the values. So let's consider the partition K1, K2, and K3. So K1 in one partition and K2 and K3 in another partition. So let us see what are the values. So we have K1 and V is, let us say, A. So we look at K1 and A. So this is K1 and this is A. So K1 and A is this one. Let's mark it. We have this plus. So what are we computing? We're computing this T of uh, K1 comma A plus T of the other partition K2 K3 comma A plus the distance between A and D. So this we have checked from the table. We have looked up 1 plus K2 K3 is how much?
K2, K3 is 6. K2,
Okay,
K3 is
okay,
6 here.
fine. So distance of A and D we have already seen 2. So this is 9. So similarly for all the 11 rest of the, so this is only one candidate for us. So similarly there are 3 into 4, 12 candidates. So each of these 12 candidates will get a value and we'll take the minimum out of these. And it turns out, uh, I mean, I will leave it to you to verify that there is actually a Steiner tree of weight 7. So there is, let me mark it.
I guessed its solution as 8. I don't know how and where. Let me do it again. So since connectivity has to be maintained among K1, K2, and K3, so definitely we have to go through these two
No,
triangles.
you're also looking at D. So you want to maintain connectivity among K1, K2, K3, and D. So you were interested in the cell corresponding to K1, K2, K3, and D.
Yes. So to maintain the connectivity among K1, K2, and K3, I mean, the first half closed rectangle has to be definitely followed, which you have highlighted in green. So 1 plus 1 plus 1, 3 has definitely needs, I mean, this much cost has definitely need to be incurred.
Yes.
And then I can maintain the connectivity among K1 and K3 by either by following this path, 1, 1, 6 by spending 6 rupees, or by going through this 2 plus 1 3 plus 1 4 plus 1 5. So 1 2 3 plus 5 8. Yes, so that is how I probably computed the value as 8.
So you have to remove this. This is not necessary. This edge of weight 3, if you do not take this edge, then you have a connected graph
Yes,
containing all the vertices. And what is the total weight of these edges if you do not take 3?
7.
Yeah, that's all. So does that make sense?
But I have a doubt here.
Okay.
So the thing is that frequently we are computing the shortest distance in between say A and the other vertices. So indirectly in the worst case scenario, we would be applying single source shortest path problem, say n number of the times, wherein n is the number of the given vertices in the graph.
Okay.
So, and I don't remember what is the complexity of the Dijkstra's algorithm. So say if it is
Then log n.
n log n kind of a thing. So
Yes.
this comes out to be n square of log n thing here itself. And then we have to explore these many number of the possibilities.
Yes.
So even though the mutually exclusive subsets of a set won't be exponentially large. So if the cardinality of the set is equal to say n, then the possible number of the mutually disjoint subsets would again be of the order of n. And we have to do this much exercise for the number of the vertices, so n square. So this DP thing requires the effort of the order of n square. And for that shortest path thing, we require the effort of the order of say n square of multiplied by log n. So, and we would be making these two efforts sequentially or consecutively. Consecutively. So therefore, the complexity of the solution is of the order of n raised to the power 4. Is this the case here? I'm not sure.
Yeah.
It's
Yeah.
polynomial.
It
Go
whatever.
for it.
So per entry, the thing is, what is the total number of entries in the table? That is the first thing we compute. So in this case, the total number of entries is number of rows into number of columns. So how
Hmm.
many rows?
So there
Total
would
number
be
of,
rows of the order of n. Like here 1, 2, 3, 4, 5, 6, 7. But we, I mean, again, so if we prepare the table here, so this is same as the previous one, exponentially large. There could be a
yes.
possibility of, yeah, becoming
So
things
then
exponentially
it
large.
is, yes. Yes. So it is like 2 to the power, sorry. So now how many terminals are there? Let us say there are k terminals. So k choose 1 plus k choose 2 plus k choose 3, like that k choose k. That is the total number of rows. Yeah. So that would be about 2 to the power k, the number of
Yes.
rows.
Hmm.
And the number of non-terminals is bounded by at most the total number of vertices in the graph.
Yes.
So that is the total number of entries, number of rows multiplied by the number of columns. And now
Mhm.
every entry, as you have rightly pointed out, that you are computing Dijkstra. you're computing distance with that given non-terminal and uh, that other value of w. So two vertices, one terminal and one non-terminal. No, no, both are non-terminals. Fine. So, but for every entry, you have to compute. You have to how many lookups you have to make. So two lookups per uh, these many things. So how many? In this case, 12 things, but that could be potentially. So it cannot be more than 2 to the power k overall. So the point is the running time is 2 to the power k times some polynomial in the graph size. So as
Yes,
long
yes.
as k is constant, as long as the number of terminals is constant, we have a polynomial time algorithm. So that is the whole point of fixed parameter tractability. So we are saying that okay, we have a fixed parameter tractable algorithm where the parameter is the number of terminals. If the number of terminals is constant, then we have a polynomial time algorithm. That's all we are saying.
Yes, yes, yes. Right.
Yes. Fine. So yeah, I mean we're not we're not going to get a polynomial algorithm if the parameter itself is very large, and that is understood, and that is the assumption uh, in all these algorithms we are looking at throughout the course. Fine. So I think we can move to the next question. We take the other question. This is relatively simple question. Okay, so I have to define what is the dominating set, or are you already aware of what is the dominating set?
No.
Okay, so let
Yeah.
me define it for you. I'll give you the book definition. So a dominating set for a graph G is a subset D of its vertices such that any vertex of G is either in D or has a neighbor in D. Let me write it down. A dominating set for a graph G is a subset D of the vertex set such that any vertex of G is either in D or has a neighbor in D. So let's take an example. So let's say this is a graph and we want to find a minimum dominating set. Of course, if you take all the vertices, that is also a dominating set. So how about taking, so can you guess what is the minimum dominating set size?
So, so I'll consider a vertex which has got the largest degree here. So say I will consider the vertex. If I include the vertex number 2, then so I'm looking for the dominating set of the smallest size. So if I include the vertex number 2, I need not to include 1, 3, and 5, and then I include
Exactly.
4 here, then I include 4 here. So this would be of size 2. So isn't isn't same as the vertex cover?
No,
The
no.
smallest number of the vertices covering all the edges of the given graph.
So you were saying that the vertex cover size is also 2.
Yes.
So what is the definition of a vertex cover?
So vertex cover is the so I'm talking about the minimum vertex cover. So the minimum set of the vertices covering all the edges of the given graph. So connecting all the edges of the given graph. So like say here, if I include, no. Here the size of the vertex cover would be, I need to consider the vertex number 2, and then I have to consider the vertex number 3 as well. So vertex cover would be 3, yes.
Because as you can see, this is a valid dominating set because every vertex is either neighbor to these two vertices or
Mhm.
itself these two vertices, but this does not cover this edge.
Yes.
So yeah,
So this is not same as the vertex cover, yeah.
correct. So this is the definition of this dominating set. So now we come back to the question. So we have a bipartite graph, and bipartite graph has two partitions, A and B. The number of vertices in A is strictly less than n by 2. Sorry, is at most n by 2. It could be equal to n by 2, but B is bigger. Let me draw it bigger. So B is cardinality wise, B is larger than A, and all the edges are going between A and B. Fine. So the goal is to find a minimum size dominating set in this bipartite graph. So let D be such a dominating set. Then which of these properties or which of these statements about D with respect to the graph is true? So first, let's look at the first question. So we'll slightly move these things to the right.
So what this NG stands for?
So neighborhood of this, so n is the neighborhood of this subset with respect to graph G. Neighborhood means
Okay.
the vertices that have connections. So a vertex is called a neighbor of another vertex is there is an edge between them.
Mhm.
Fine. So we have a dominating set. So the dominating set D has vertices. Maybe some of the vertices of the dominating set are in A and some of the vertices are in B. Or maybe all the vertices of the dominating set are in A and maybe the other thing is also. So let us say that some of the vertices are in A and some of the vertices are in B of the dominating set. The first statement is saying that if you consider those vertices which are in A and in the dominating set, then the neighborhood of these vertices is of course a set of vertices in B is a subset of A. So that makes no sense, right?
Uh, yes.
So what is D intersection A? It is a set of vertices here in A. And what is the neighborhood of D intersection A? Some vertices in B.
Some of the vertices which are there in B won't be considered here because we cannot have common vertices in A and B.
Yes.
So therefore, this will be the subset of A. This is true. This is true.
No. Why is this true? Come again. Why you think it is true?
Because D intersection A, so D would be having either the vertices of A. So D is the dominating set of the graph G, so it would either be having the vertices of A or the vertices of B, uh, some of the vertices of B, because quite possible that A could be the neighbor of the sum of the vertices of B. So therefore, the cardinality of the D intersection A would be less than the cardinalities of the individual sets here, either of A or B. It would be smaller. So
Okay.
since it would be smaller, so therefore this will be the subset of the set A, I think.
So the cardinality, let us say I understand what you're saying. So you're saying that this subset, D intersection A is a subset of A. And therefore the cardinality of D intersection A is smaller than the cardinality of A. And because the cardinality of B is larger than the cardinality of A, therefore the cardinality of this B intersection A is also smaller than the cardinality of B. But that doesn't say anything about the subset relationship. Subset means all the vertices in this part are contained in A. So
Hmm.
let's revisit the argument. So D is a dominating set. So that means there are vertices either from A or B, and all the other vertices are neighbors to some vertex in D. Now, D intersection A is the set of those vertices in the dominating set which are in A. Now, what are the neighbors of these vertices? The neighbors are lying inside A? No, it is a vertex, it is a bipartite graph. Therefore, in the bipartite graph, within the same partition, whatever vertices are there, they are forming an independent set. There is no edge between two vertices in the same partition. So therefore, all the neighbors of D intersection A are somewhere in B. So this set is actually a subset of B. Isn't that true?
Uh, See, so I actually could not understand this
Okay.
because D intersection A means the elements which are common to D and A. So D would be having, let us assume, say D is having the, so let us assume that all the elements of, so the clearly this because D is having all the vertices of A
No, no, no.
and
D may have some vertices from A, not
some
all.
vertices of A, and not all, and some of the vertices of B, which are the neighbor of the vertices of A,
Correct.
right? So since some of the vertices are the part of D, and if I take the intersection of some of the vertices along with the full vertices, so the result would be sum of the vertices.
Yes.
So the sum of the vertices, and then I compute the okay, I forgot to apply this ng operator here. Then I compute the neighborhood of those
Yes,
sum of
yes.
vertices. So the neighborhood of sum of the vertices will came out to be sum of the vertices of B. So sum of the vertices of B clearly would be the subset of B. Yeah, it's correct now.
Yes, yes. So you are only looking at D intersection A and saying that okay, they are part of A,
Yes, yes,
but
yes,
you're not taking their neighbors. Okay, fine.
yes, yes, yes,
Okay. So you're we are saying that all the neighbors of D intersection A are actually in B.
yes, yes. So second option is correct.
Yes. So second one is true. This one is false. Okay. So let's look at the next one. The next one is saying that okay, you look at some vertices of B. So you remove those vertices of the neighborhood of D intersection A. So let me just do some color coding. So let us say these black vertices are part of the dominating set. So these black vertices are in fact T intersection A, and let us say their neighbors are marked with green. So let's or maybe blue. Yes. So the neighbors of these guys are blue. So these blue guys are in the neighborhood of T intersection A, and you from B you get rid of these blue vertices. So you are left with, let us say, some red vertices. These red vertices are basically this entire thing exists in B, but not in the neighborhood of these black vertices, which are the intersection A. So now the claim is that these red vertices are in fact a subset of the dominating set. So do you
Uh,
understand the claim?
Yes, yes. So if we include all the vertices of the set A as a part of the dominating set, then clearly we need not to include these the blue ones, because these are the neighbors of these elements of A. So then
Correct.
we are left with the red ones. So now this D comprises of the set A plus these red ones. So yeah, and yeah, and if I take the intersection of D, so the neighborhood of this will come out to be these blue ones, and if I remove these blue ones, so basically the question is that whether this red are the subsets of D or not. So my answer is yes, they would be.
Okay. Okay, so let me give it a thought. Yeah, this is correct. Because if it is a dominating set, and so we can go by contradiction. So if there is a red vertex, that means the vertex which is in this side. And if let us say it is not in the dominating set, then it is not even neighbor to any of the vertices in the dominating set. So that then the definition of dominating set will be violated. So that's why this is correct.
Yes.
Okay. So let's look at the next one. It says that let dA be one of the 2 to the n minus 2 possibilities for D intersection A. At most, it should have been at most. Okay, so see the size of A, the cardinality of the set A is at most n by 2. That means the cardinality of the power set of A is at most 2 to the power n by 2, isn't it?
Yes.
So
Yes.
let us, this should be at most 2 to the n by 2. Okay. So let D sub A be one of the 2 to the n by 2 possibilities for D intersection A. So you are just looking at one of the subsets of A, and this is one of the possibilities. I mean, one of the candidates for the inclusion in the dominating set. Then this subset of A, dA, union B minus the neighborhood of dA is definitely a dominating set for in G, but it may not be minimum, not necessarily minimum. So that is the statement. So let me redraw the figure, or maybe this figure is sufficient. So let us say that dA is these black vertices. So this set of black vertices is dA. So it is a subset of the dominating set. Okay. So maybe there are other vertices in the dominating set. So let's do one thing. So let us say that, so let us mark it with a different color. Let's take green. So let us say that these two vertices are in dA. Okay. These two black vertices which are encircled in the green ellipse is in dA. So the statement is dA union B minus the neighborhood of dA. So the neighborhood of dA has this, this, and this. So if you take all the vertices in B which are not in the neighborhood, other than this everything else, and this thing, then essentially you have got a dominating set. But it is not necessarily minimum. So first let us decide, uh, let us determine if this thing is a dominating set.
So I think that this statement C is true under the condition that the cardinality of the set B is higher than the cardinality of the set A, which is the case here in the problem. So since the cardinality of the set B is higher than that of A, So if I include all the elements of the set A as a part of the dominating set, say in the worst case scenario, so then I will, so I would
Right.
be left with what? Something bigger minus n by 2 to be included to make it the part of this thing, right? And
Yes.
yes,
So yeah, you're right. So if A was very large with when compared to B, then if you take all the elements of A, then basically you are not taking a dominating set because B is smaller and taking B itself will become a dominating set where we can assume that the bipartite graph is connected. So because A itself is smaller and you're taking a small part of A and everything that is not in the neighborhood of that small part, then of course it's a dominating set, but there is no guarantee that this is a minimum dominating set because yeah, probably you could take some other subset of A and that would have less, that would have covered many neighbors in B. So there is no guarantee that any subset of A will give you a dominating set when you apply this formula.
yes.
So this one is correct. Let's mark it too.
And last one is the opposite of it, I think.
So let dA be one of the at most 2 to the n minus 2. There should be at most n minus 2 possibilities for D intersection A such that B minus the neighborhood of this set is minimum. Then this thing is a minimum dominating set. So this is characterizing that okay, you take that subset of dA such that in the neighborhood of dA there is a lot of elements. So that B minus dA itself is very small. So you are taking a very small number of elements other than dA. Then are you going to get a minimum dominating set?
Yes, this is true.
So this we have to check.
Because after including all the elements of A and the cardinality of B is greater than that of A, so if we are left with minimum number of the elements, uh, so this will result into a minimum dominating set.
Okay, let me give it a thought. So you're taking that subset of A such that in B, there are not too many elements left to be covered. In fact, in B, only the minimum number of elements are to be covered, and you pick all of them.
So consider a case wherein the cardinality of A and B is equal.
Okay,
So if A and B is equal and every element of A is connected to every element of B, say, so then the cardinality of the dominating set would be equals to that of A.
okay,
So which is the minimum one? I mean, we cannot
fine.
find yeah, better than this one.
That is fine. So I want to see if I can construct a counter example that will invalidate or falsify this statement. Let's do one thing. We have a few minutes. Let's spend some time on it. Now, if you have all the things, then that is a problem. No, wait, this is not going to help. Now, let's do one thing. Let's take 4, 4. Okay. One of the 2 to the minus 2 possibilities are that this one is minimum. And then you take, that is the problem. That is the problem. Now I got it. Okay, let's, yeah. So here is an example. So here is an example that will falsify this statement. Okay. So consider DA as 1, 2, 3. This is a B. Ah, this problem. We want, so we will get rid of this. Let's do this. Okay. Actually, this is uh, this is not the content. Oh, we can make it 2, 3, right? Let's how about this? So 1, 2, 3, but this is also the conveyor. This should work. So, so yes, now this will work.
Okay, so here DA is 1, 2, 3, and V minus this thing. So V minus this ng thing is all 0. So I mean this thing is 0, which is minimum.
Yes.
So therefore the entire dominating set is equal to 1, 2, 3.
Yes.
So that's correct. I mean this statement is true.
Uh, this looks good. Right. Wait. So, entire dominating set is 1, 2, 3, right? I wanted to do something like I wanted to get 1 and 2. So I wanted 1 and 2 to be the dominating set, but that is not possible. Okay, so we'll add one more element. We'll add one more element. So just delete this. So, and now let's do one thing. So we want C everywhere. So this is, so we want C everywhere. Okay.
So yeah. So this time I won't be taking DA as 1, 2, 3, 4. Rather, I'll take 1, 2, 3 because I have liberty to take any one out of 2 raised to the power n by 2 number of the possibilities. So I'll take 1, 2, 3 from A, and then whatever remains here is, so D is remaining. Then I will take D. So then the union 1, 2, 3, and then D is the dominating set here, and its cardinality is 4, and which is the minimum one.
But how about 1, 2, and C?
How
Is
about
this a
C? One.
dominating?
How about
This 1, 2, and C, is this dominating set?
one, two, and then C? Okay. So if I take one, two, so one and then two, and yes, yes, you're right. But here, so what this B minus? So therefore, this B minus the AB. So this is CD, and which is not the minimum one. So
So
the
what is your
minimum.
DA? My DA is 1, 2, 3, 4, and
So, yeah. So DA is here. DA is 1 2.
okay. If your DA is 1, 2, then you
Uh-huh.
get rid of everything else. So
So DA is 1 2. Yeah. So that is a minimum set. Even in this case also.
we have made some mistake, it looks like, because see, 1, 2 is not a dominating set, because what is the definition of dominating set? It is saying that any vertex of G is either in D or has a neighbor in D. So 3 doesn't have a neighbor in 1, 2. 3 has only one neighbor, that is C. You have to take the neighbors. You have to take 1, 2, and the neighbors of 1, 2. So what is this thing? You don't have to take the neighbors. You don't have. What is? We made a mistake. Looks like. So we earlier said that this is true. So we said that take any subset of A. So 1 and 2 is a subset, and take the union of this with B minus neighborhood of DA. So that is a dominating set. We said that is probably not right. So I think this is not right. So you understand the problem. So if you take 1, 2, then you are covering all the edges which are connected to 1 and 2. But sorry, all the
Mhm.
vertices. So you want that, forget C now. So your DA is 1 and 2. Your DA, your subset of A is 1 and 2. That's what you said.
Mhm.
So now we have claimed that DA union B minus neighborhood of DA. So what is the neighborhood of DA? Neighborhood of DA is everything in B.
Mhm.
So B minus neighborhood of D is 5, empty.
Mhm.
So this entire thing is nothing but 1 and 2. DA
Right.
union B minus neighborhood of D is 1 and 2. But 1 and 2 is not a dominating set because this vertex 3 is not in 1 and 2, and it does not have a neighbor in 1 and 2 also. Similarly, 4 does not have a neighbor in 1 and 2 also.
Mhm.
So I think this statement is incorrect.
This is incorrect, and the last one is correct.
The last one is also incorrect. For example, in this case, you have 1 and 2 as DA. So you have 1 and 2 as DA. So the last statement says that you pick that DAs for which this neighborhood of sorry, B minus neighborhood of D is minimum. So neighborhood of 1 and 2 is the entire set B. So B minus neighborhood of B is actually minimum, and neighborhood of DA is actually 5. But this is not even a dominating set. Forget minimum. So 1 and 2 is not a dominating set. That is our observation.
No, one and two is dominating set because either one or two or its neighbors. Yes, one and two is not the dominating set. Right, right, right. Because three and four have not been covered. Right, correct. So yes, this is
So
also false. Yeah, right. True.
this also looks false.
Yeah.
So
I
in the
misinterpreted this definition of the dominating set. Yeah.
So in the previous year's offering, they marked this as true. I think this is incorrect. So I am saying that this is false, but they marked it as true. That's why I was carried away and I declared it as true. But I will recheck this. I believe that this is false because we have a counterexample.
Yes. So is this possible, because I missed first two sessions? So is this possible that in the next session you gave a very brief overview of kernelization thing, or you take one simple question on the kernelization, just one question, so that this term
Yeah,
become.
we can do that. You can look at the video, or I can also spend 10-15 minutes on kernelization.
Yeah, yeah, that would be fantastic. Yeah. And thank you so very much for uploading notes and the videos. So before this session, I could review the notes of the previous meeting. So those
Okay.
notes were very, very helpful for me.
Right,
Yeah,
right, right. I will upload this one also. Thanks for
yeah,
reminding me. I will do it.
yeah. Thank
Yes.
you so very much.
All right then. All right then. We'll close for today.
Yeah. Good night. Thank you
Okay.
so
Good
much.
night. Thank you
Bye.
for
Bye.
joining. Okay. Bye.